Based on the past, a company knows that an item produced by a highly experienced machine operator, which we're calling E1, so the event E1 is the event that this particular object was made by a highly experienced machine operator, will have a defective rate of 1%. Items produced by somebody with some experience have a 2.5% defect rate, and new operators, which we're calling E3, have a 6% defect rate. At any one time, 60% of the items are produced by highly experienced operators, 30% by those with some experience, and 10% are new operators. Find the probability that a particular defective item was produced by a new operator. Okay, so we're being asked to find, we're basically being told that we have a defective item. We're being asked that it's produced by a new operator. So we're saying we're given that it's defective. So D here, I'm making the event that we have a defective item. And we've already defined, or E1, E2, and E3 have already been defined for us. So we're trying to find out what is the probability that if we have, for a given defective item, what's the probability it came from a new operator? In other words, what is the probability of E3 given D? And if you look at each of these individual probabilities as you're reading through this, let's see, an item produced by a highly experienced machine operator, which we're calling E1, will be defective 1% of the time. So that is what is the probability that it's defective given that it comes from E1. Similarly, so that's the, let me just restate that. The probability of D defective given E1 is 0.01. The probability of defective given that it comes with somebody with somebody with some experience, that's a 2.5% defective rate, so 0.025. And the probability of defective given E3, we were told, is a 6%, 0.06. We're trying to find the probability of E3 given D, or we're given probabilities of D given each of the experience. So you can see we're trying to flip this this condition around. We're given the condition of E1, E2, and E3, and we're trying to flip it around and get the probability of E3 given D. This is exactly where we use Bayes' theorem. So in order to use Bayes' theorem, I need to set this up as a tree diagram. So first off, I'll say the probability of E1, probability of E2, and probability of E3. And you may be wondering why I'm choosing to split it up based on E rather than D. It's because E is essentially our first event. You know, when we're talking about these conditional probabilities, we talk about the order in which things happen. Essentially, we're deciding that it comes from we're deciding it comes from a highly experienced machine operator, and then we have the probability that it's defective given that it's from the highly experienced machine operator. So this, in effect, has the first in our timeline. It happens first. So then we can say, okay, the probability of D given E1 is 0.01. Similarly, the probability of D given E2 is 0.025, and the probability of D given E3 is 0.06. Now, I could fill in more of these numbers. I could fill in the probability of D complement given E1, D complement given E2, and D complement given E3. But actually, a lot of times when we're doing Bayes' theorem, we kind of actually don't feel the need to do the entire tree. I'm going to leave a little branch to show that there's stuff I'm leaving off of this, but I'm really only concerned with where the items are defective. So you can see if we go up in this branch, we have a defective item. If we were to go down, we would have a non-defective item, or a good item, however you want to define that. But I'm not really interested in that time. I'm more interested in when the items are defective, because that's the condition of this conditional probability I'm trying to find. So let's see. I'm wanting to figure out what these three branch probabilities are, because these are the three branches of the tree where I have defective items, and I'm going to need that for my law of total probability. Okay, so let's see. The probability of E1, we know that 60% of the items are produced by highly experienced operators. So if you have an item, there's a 60% chance it came from somebody with a highly experienced person. There's a 30% chance it came with from somebody with some experience, and a 10% chance it came from a new person. So multiplying these together, we get 0.006. I should probably actually plug that into my calculator. 0.3 times 0.025, which gives us 0.0075. And this one is also 0.006. So we've constructed the tree diagram. I know the instructions say to give all the probabilities, and I could figure out these other branches, but like I said, those branches we're not going to be using those because those aren't part of the, well, they're not where we have defective items. Also, because we're not doing the entire tree, you'll notice these do not sum to 1. If I did these additional 3 branches on here and then added all of this up, it would sum to 1. So in any case, the law of total probability says that if I look at this tree and I look at all the different branches where I have defective items, that is this branch, and that branch, and I add these things up, this will give me the probability of D. So 0.006 plus 0.0075 plus 0.006. That plus 0.006 plus 0.006 gives me 0.0195. So overall, the probability of getting a defective item is 0.0195. It's almost a 2% chance of getting a defective item. And that's probably not that surprising. You know, there's a 1% chance if it comes from a highly experienced operator. 2.5%, that's actually really close to the 2%, almost 2% that we see is the average. But new operators have a notably higher defect rate. So this is kind of, yeah, that's really a weighted average, if you want to think of it that way. All right. So finally, I want to use Bayes' theorem to figure out what is the probability of E3 given D. So what is the probability, if we know we have a defective item, what's the probability it came from this bunch right here? And that is taking that branch divided by the sum of these 3. We already found the sum of those 3. That's the 0.0195. So I'll do 0.006 divided by 0.0195, which gives me 0.006 divided by 0.0195, which gives me 0.3077. So the probability that it came from a new operator is almost 30%. Looking at these, that actually, you know, my intuition kind of agrees with this. 0.6% of the total items are defective and they come from experienced operators, and also 0.6% are defective and they come from new operators. It's interesting to see that this and this number are the same. That's because the new operators, although they have a lower defect rate, they're producing a lot more items. So overall, the number of defective items they produce equals the number of defective items the new producers produce. But the people with some experience, they produce more than the new people, but they still have a higher defect rate than the experienced people. And that kind of, when we multiply those together, you can see more of the defective items actually come from those with some experience than from either of the other two camps.